Hello again, I'm Deacon Anthony. Welcome back. We are now going to be considering modern technology and how it applies to the calendar and in particular to the determination of Pascha. And we will, of course, be carrying along the theology that we considered. At the end of the last part, I offered as a meditation some words from Vladimir Losky about the interplay between contemplation and action. And in this phase, we will certainly be moving into the action part. Modern technology is certainly at the forefront of the Aleppo proposal. And this is a screenshot I took of the webinar given by Keir Job back in April. And he is showing here the several pages from the Shambhasi proceedings where that astronomical data was reported. That was back in 1977. The date on the publication is, I believe, in 1983. Interesting that one of the contributors who had submitted a very informative paper was Professor John Erickson of St. Vladimir's Theological Seminary, who is now with us at this conference and presenting as Father John Erickson. To put what we are going to consider in the context of the first part of my talk, we are now at this phase, number 3, modern scientific and astronomical. And also there is this fixed non-Nicaean date for Pascha that would be somewhere in April on a Sunday, between certain dates. And while it certainly doesn't totally abandon all that happened previously in the many hundreds of years, it is a significant departure in that it now makes Pascha to be just another calendar date that is observed and moves around from year to year. I mentioned this paper before, and it's a very good paper. I don't want to appear to be picking on the author. I recommend it. But there are a few things to point out, and one of them is just from a historical point, is that Jeremiah II of Constantinople, and right after was contacted by the reformers and by the Pope's representatives, but the proposal, the Gregorian reform was condemned in a series of sigilia in the late 16th century from Constantinople. But that's a part of history, the whole history that really needs to be looked at in much greater detail. But moving down here, the two references that I used were from this paper, and I didn't consider Ambrose of Milan because I thought the whole reference was a bit spurious. It was reported incorrectly, I believe, that this is where I found it, if I have it right. But we did talk about the one from John Chrysostom, and one of the things, of course, was, well, is it really him? But let's just say that we take the words that were given, and there was a little ambiguity about what was meant here, about after this. And that is to say, is that a logical after or a chronological after? If it's a logical one, okay, he's just marking things that, well, we think about this and that. That's okay. If it's chronological, then it doesn't allow for dates that are permitted in the present calculation of both the Julian and the Gregorian Paschalian. But that's not what the complaint is here, is that Roman Catholic practice does permit occasional coincidences of the full moon, and hence 14 Nisan and the Jewish Passover with the Sunday of the Feast of the Resurrection. So we have the full moon, but which one? Is it the astronomical full moon that we're talking about? And we also saw that in the biblical narrative, full moon is a very nebulous thing. And then here is the 14th of Nisan. That's the 14th day of the moon, and the Jewish Passover. But now, which one? Because if he's referring to modern calculations, there are modern rabbinic calculations of the Jewish Passover. That's done using a computus, and the equinox, and it's so something in the same category as the Julian Paschalian. It's not quite as much an error, but certainly much more so than in the Gregorian calculation. So we have at least three different concepts here, and this full moon, of course, could be the astronomical full moon. So four different concepts, I guess. And the question now is, how do we put them on the same level with regard to reporting of data and making a valid comparison? He gives us this date of 1981 that he finds is troublesome for the Gregorian calculation, and that is contrary to patristic practices because of the occurrence of the full moon on the date of Pascha. But first, let's take a look at this in the old Paschalion, and we're going to just apply the methodology shown us by Akir Job. If we do that for 1981, we come up with 3 for the golden number, that's this column, and 13 here for those 28 years of the cycle that Pope Gregory referred to. And if we just see where they intersect, we come up with 13 April as the date on the Julian calendar, which is 13 days behind. So to put that on the same reference frame that is used for the Aleppo calculations and the Gregorian calendar, which is the Gregorian calendar, we need to have 13 days, and so the Julian comes up as April 26. So going back just again, the lunar here, and the solar here, and at the intersection, 13 April plus 13 gives us the April 26. Now, in this table, the occurrences with the Passover are noted by the particular code being put out here in the margin, and it's just for information. Really, it doesn't affect validity. But just to note it, that in fact here the Gregorian P is agreeing with the date of Passover. Here's the Passover date, and here's the date for the Gregorian. But sometimes the astronomical calculation is going to do that. And here is the date for Passover in this year, the year 1974, which is agreeing with the Q, agreeing with the Passover on April 7th. And one of the questions then too is, as we looked when we built up our biblical calendar, is, well, what does that mean? Because he's reporting this is looking at the 1981 as April 19th as being the date of the Passover, and is day 1 as the Nisan 15. But it could be looked upon as the Passover event, which is occurring here on that time right in between. So this is a standard way of reporting it, but we should remember that when we go from the civil day to the biblical day, there is a difference because there's an offset, and we saw that when on the calendar that was constructed in the first part of the presentation. But what has happened here is that the Julian, with that offset, actually agrees with the scientific calculation from Aleppo, giving April 26. Of course, the Julian date, day on which this in the Julian calendar is the April 13th. So it's something really different, but this is the correct comparison. On the other hand, the Gregorian is here at the 19th, which is the day of the full moon. However, if we remember back on that comparison slide for both the Julian and the Gregorian Paschalia, we saw that there were limits as to what that allowed for the dates of Pascha. And it turns out that the latest date we found was April 25. So if the Paschalion of the calendar is being true to its methodology, you cannot go beyond this date of April 25th. And so that is what has happened here. The Gregorian and the Julian, if it was on the same correct time frame, could not possibly predict a date of the Pascha beyond April 25th. And that is, in fact, what has happened here. Now, It's valid, certainly, for the astronomical calculation. I mean, that's just what it is. However, one of the things in the preceding phases was that those limits on the date of Pascha were very, very important. And it was almost for sure that if you were outside of those dates, you were going to be wrong. So I'm not saying that this is wrong, but rather it shows here that for the detailed scientific calculation, dates are allowed that would not be allowed properly within the Julian or the Gregorian. And the only reason why the Julian gets this right is because we have to make that ad hoc correction of 13 days, and it gives the appearance of being a match. In fact, it's not. So this limitation and the others that we looked at is a consequence of applying in one form or another the Metonic cycle, which produced those 19 possible moon entries indexed by the golden number. And also with regard to the both the Gregorian and the Julian, they are based on not necessarily the full moon, but on the 14th day of the moon. And we saw that when looking at the bull of by Gregory the 13th for the Gregorian calendar, and then all the times that the 13 and the 14th rather was mentioned in the patristic commentary, and then also in the biblical verses that we looked at. So that was a warm-up, and now we're going to get into a consideration of astronomy and what we need to know in order to understand these new calculations that are being made or have been made. And there was a saying, dates from the 1940s, I understand, but it was very popular some years ago. I don't hear it that much now, but it says, if you talk the talk, you got to walk the walk. And so that's what we're going to do now, and I had to do it. I'm not an astronomer, but I find that it's very interesting to put the dating method and what's considered in the context of modern astronomy. Here is the part of the solar system that is the sun and the earth, and the sun is here at the foci of an ellipse, one of the two, and the orbit of the earth is elliptical. This is actually drawn, and none of this is drawn to scale. The actual orbit is very close to being circular, and that orbit and the Earth-Sun orbit defines something that is called the ecliptic, and the Earth is tilted as it goes around. Let's see, it looks like like this. So it's tilted this way, and it spins around that axis counterclockwise, and then revolves around the sun counterclockwise. That's really easy to remember because that's how we process. In church, we go for the entrances, we go around the holy table counterclockwise, and then we go out to the church when we have processions outside, and we process around the Chram, the church building. We go counterclockwise. I understand that was a matter of controversy, I think, with something about the old believers. But anyway, that's the way we do it, counterclockwise, just like the Earth. This orbit ecliptic is a plane that contains the Earth and the Sun. It's like a flat disk. There is the Earth's equator, which if that is expanded infinitely or throughout the cosmos, it is known as the celestial equator, and we'll encounter that. And as the Earth moves around, tilted like this, it goes through a point closest to the Sun, called the perihelion, and farthest away, called the aphelion. And I like to think about this as though you're standing here and you're tilting yourself. Your head is tilted this way, your feet this way. And so at this point, the sun is shining more on your feet. And so that's the winter solstice. Now, as we go around, this orientation doesn't change. It's always pointing in this direction. So when we're over here, the head and the feet are the same, but it's like your shoulders are getting the sun. Then you keep walking, you have to walk around backwards, a little awkward, but you get here to where you're almost at the aphelion, not quite there, the farthest away, but here your feet are farther away and your head is closer. And that's getting more of the sun, so that's the northern summer solstice when it's hottest. And then back around again here to where it's on the side, it's on the shoulders. That's kind of a crude way of looking at it, but there is a precise definition for the equinox, and that is, I use this one from the United States Naval Observatory because it's very concise, and it talks about the actual apparent, and that sounds so contradictory, but it means what you really see is observable. The motion of the sun as seen from the earth, so it's from the perspective of the earth. It's a precise time at which the apparent ecliptic longitude of the sun is 0. This precise time shifts within the civil calendar very slightly from year to year. So what does that mean? Well, one of the things that I found astronomers like to do is not to again, this is not a scale drawing, but not only not to scale it, but to just do it in terms of geometric representations that show orientations very clearly. And so that is what is done here, because what we need to do first, this reminds me, and the viewpoint that I like to use that makes sense to me is that one of the first things we're going to do is take the Earth, which is going to be at the center, and we're going to straighten it out. And when that happens, what happens is that this ecliptic now is going to be at an angle. So the Earth will be straight. We're going to straighten this out, and then the ecliptic will go at an angle. Let's walk through those steps just to be clear. Here's the tilted Earth. We're going to straighten it out. When we do that, all these rotate, the ecliptic tilts, and we wind up with the Earth's axis straight up and down, and it looking like this. And when that happens, and when we do that, we construct this. So what we did was, remember, we tilted the ecliptic, and I have to apologize. This is, I didn't have a chance to redraw any of this, but the orientation here should be really rotated, because this point refers to this over here. Everything is correct. It's just that the two pictures don't quite show it in the same orientation. However, what we have is that equator, which is the Earth's equator, which is the celestial equator now. So that's straight, and that's this disk here, which have expanded throughout the cosmos. It becomes the celestial sphere. So we're seeing everything from the perspective of the Earth. And so we say these things. Of course, the Earth is not the center of the universe. Well, it really is, from the point of view of perspective. And it's just that if we look at things, for instance, the solar system with the Earth as the center, all our equations are a lot simpler. They're much easier to see what's going on. However, we see everything, and astronomy looks at this from the perspective of the Earth. And so this ecliptic was now tilted because she straightened the Earth out, and that's this 23.5 degrees. And we see the Earth now that from this perspective on a yearly basis, the sun occupies these various positions. And when it hits here, and again, this always seems very clear to me, when the sun is here relative to the Earth, what we see, it's shining down on the north and the northern hemisphere, and so that's the northern summer solstice. And then as it comes around, it intersects the celestial sphere, goes around to here, which is winter, and then comes back up on this, is referred to as this northern journey, and then at this point of intersection is the vernal equinox, and that's the definition, given a little bit differently here, but it's that same perspective. There's a story I like to tell. I was taking a course some years ago, and we were looking at a text in Ecclesiasticus, and in the Hebrew, it's that makes no sense whatsoever. It talks about the sun going in and out and doing stuff, and so I reported, I had looked it up, and in the critical apparatus, it was something from the Septuagint, which interpreted it, and it was very clear. It talked about the sun going from north to south. And So I reported this in class, and one of my fellow students scoffed at me that, of course, the sun goes from east to west, not north to south. But I assured him that it was the case, and I observed it myself. I have a window that faces roughly due east, and I would observe that at one point over here, when the sun is over here, it's all the way over to the right, way down south. And then as it travels up, eventually around, and this is around December 21st, and here around March 21st, it's moving to the left, about the middle, but then it keeps going. Eventually, it gets all the way over to the left, and that's at the summertime. And then, of course, it goes back. So, in fact, the sun does go, from the perspective of the Earth, does go not only from east to west on a daily basis, but it goes from north to south to the north on a yearly basis. I need to correct two things that I said. One of the beauties of the virtual presentation is I can come back in and make this correction and stick it in. And I said when the Earth is the center, the equations are simpler. And of course, it's when the sun is the center, the equations become simpler. They're ellipses. And for the ellipse, there are two foci, one of which, one focus, is the sun. Actually, let me be even a little more precise, and it goes to show how you can parse things so finely, scientifically, that in fact neither the sun or the Earth are at the center here of the orbit, but something called the barycenter. And that is dependent upon the masses of the two bodies that are revolving. If they were equal, the barycenter would be centered in the middle of the axis that connects them, and they look like they're rotating around that barycenter. Now the sun is so massive by comparison to the Earth that the barycenter is almost close to the center of the sun, and so we allow that residual in the consideration, and to simplify our understanding and our model, we just say that the sun is at the focus of the ellipse for which the Earth is revolving. I should add also that in this picture, the orientation here, of course, this is north and south, but east is this direction. The east always points to the vernal equinox, and so if you're looking at that from this perspective, then this is to your left. March 20th, 2022 at 11:33 a.m. Eastern Daylight Time. What were you doing? You have to correct that for your particular time zone. Many were asleep. It was a Sunday, a very convenient time here on the Eastern Daylight Time, where we are in Baltimore. And it was a Sunday, so it was the third Sunday of Great Fast, as a matter of fact, the veneration of the Holy and Life-Giving Cross. And at this time, I was probably something with regard to liturgy, either preparing or coming from or going to. We have a very flexible schedule, unfortunately, for our liturgy. But at that particular time, I really can't tell you exactly what was special about it. However, at that precise time, to within minutes, this definition was happening, and that point was being reached, that unique point, that crisscross there at a precise time, and that happened all over the whole Earth at that very instant. It's truly a unifying event, a cosmic event, and yet it is of such small consequence to us in terms of our perspective on a daily basis, the rhythm of our life. When they occur, it is at the same instant over all the Earth. The equinox, the new moon, called conjunction, is 0 degrees, where the orientation is sun, moon, earth. The full moon, astronomical, which is opposition, is 180 degrees, where the orientation is sun, earth, and moon. And so it is not a case of at what time does the equinox or the new moon or the full moon occur, but when the equinox or the new moon or the full moon occur, what time is indicated on your clock. Our clocks follow God's clock, not the other way around. So lunar 14 is for the moon, and this shows two things. One is that the Luna 14 that we look so much at in the biblical considerations is a day. The new moon and the astronomical viewpoint and the full moon are an instant. And they also have this very neat term, syzygy, meaning they line up. So we need to take a look at some terminology to try to explain what that it means. And these are my terms and concepts, but I took this line out of a very well-known astronomical book by a very well-known astronomer, Jan Mios. And he says the accuracy needed in a calculation depends on its aim, and that's important. So I started to put together terms that I've used in my professional life, not astronomical, just scientific. And this again is one of those where the slide blossomed because I kept adding up more and more. Oh, we need this, accuracy and precision. Everyone talks about. Then there's this sense of when I do calculations, you can have a residual, and that could be okay, because you have to set a certain tolerance for what you want in terms of accuracy and precision. However, if that residual becomes too big, then it becomes an error. These can be relative or absolute. And let me skip over this one for a minute, and then we can round or truncate. We can extrapolate beyond the data or interpolate within the data. And there's limits that we set. Limiting cases we consider, significant figures, averages, biases, sensible and apparent. Those were terms we use, scientific terms actually, not necessarily mathematical. This one of granularity, I think, is a very convenient one, and it's something that gives us the right perspective for comparing different viewpoints. So what's an example of this granularity? How does it work? What does it do? Well, if I look at this year overall, what do I see? What are the chunks that I see? A granularity is a chunk. And the chunks that I basically see are months. I see 12 months. However, if I look at one particular month, then I may see a granularity like this, and I'm saying, well, that's the days. I'm seeing a granularity of days. If I go even further, if I have a diary or a appointment book, then the granularity might be hours, or it might be even half hours. And so how does that relate to our astronomical and biblical considerations? Well, Luna 14, the 14 for the moon, is a day. When we read the biblical accounts and then the patristic and even the bull for the Gregorian reform, it spoke about the days. And on the other hand, the modern scientific viewpoint is an instant. And so we have two different kinds of granularity here. The other thing is, just to point out that this name, the syzygy, interesting for when the orientation for the straight lines. So let me do an aside here in the interest of time. The proceedings from the 400th anniversary of the Gregorian Reform have a number of very interesting papers. And in one of them, the professor, he's speaking about a comparison with the results of Professor Lederle, whose results we looked at before in those pages from the Synodica 5, Shambesi, and which he references. And he's saying that we can do those for the modern astronomical data. Clavius did it himself with what he had available. And that's interesting, but the point with regard to granularity here is that he is drawing attention to this sense that the new moon after 6, how is it going to be reported? And he says that he's not sure with regard to the Gregorian calendar nor with Professor Letterley's work. And what he's saying is that here's 6, roughly, after 6, and that if that's what's here on the for the biblical day, it should actually be reported for the next day. So that gets a little tricky, and as to how that's done, and when we do comparisons with regard to the different granularities of the calculations. Also, this is, let me go back here. Who's this Ignatius guy? And that's the ex-patriarch of Antioch of the Syrian Jacobite Church, who arrived in Rome, was welcomed eventually when he was found to be legitimate, and actually was a member of the commission. And of course, I think Antioch here, we're thinking Persian and Magi, those who looked at the stars. So he had a great deal of expertise in that respect. And so what we can say is that the East was represented in that reform. In terms of one person, is true. But the East was represented, just not the Byzantine East. Ignatius was one of the signatories of the document that was submitted to the Pope for advancing the Gregorian reform, and it is said that he signed in Arabic and Chaldean. Another example of granularity is the time zones, where civil time changes abruptly as you move from one zone to another. And while that makes life easier, it does not reflect the even movement of the Earth's rotation. And so within each time zone, there's an error, and we accept that the imprecision in our clocks is a residual that we can live with, and so it's not an error. We can now move on to the data in the Synodica, and armed with our knowledge of astronomy and definitions, we now know what the scientists were speaking about here with regard to the calculations they did and the celestial longitude of the sun, and the same for the moon at 180 degrees. So it's the opposition, the full moon, but there's still a need to choose a certain meridian. And the concern is, well, what happens before or after midnight between Saturday and Sunday? And the reason is that meridian implies time. And so the meridian that was chosen recommended by the Aleppo statement was the meridian of Jerusalem. And of course, the meridians are the longitudinal lines, they're here on the globe, going from north to south. And there's a reference point, and the prime meridian, it could have been anywhere, but it happens to be right here. And so from that reference point, we look at the different time zone increments to either side of it. And we're going to be looking at the one for Jerusalem, which is in this time zone right here. And again, the meridian implies time. So the degrees here is a distance. It's a longitude, and across from one longitude line to the other, and that implies a time of an hour. And so if we now look at the time here for Jerusalem, which for the month of March or April, around the time of Easter, would be Israeli daylight time, and it's the reference point here, the universal coordinated universal time +3. So we're looking at this row right here, and if we're over here in the blue, right before the midnight, we're in Saturday. However, everybody in the red is already in a Sunday. And on the other hand, if we're over here on Sunday for the Jerusalem time, then all the values here in the blue would still be a Saturday. An example of how this can make a difference of a week's difference is if it were 6 o'clock here in the Israeli time zone, and this is the time of the Paschal full moon, that occurs on a and that would occur on a Sunday, then the rule of Nicaea says that the Easter would be the following Sunday, and so that would be a week later. On the other hand, if my time zone were to be used, and that's here UTC +4, well, that's occurring on a Saturday. And so if that time zone were the standard, then that prediction would be that the next day, the following Sunday, would be Easter. Another way granularity can come into play is in making a comparison between the modern approach, the astronomical approach, where the new moon and especially the full moon are considered to be in an instant, versus the traditional Paschalian, even the biblical viewpoint, where that 14th day of the moon is a day. And I had shown this before, and that I maintain that the traditional method spanning Nicaea to medieval and even used today, 4th to the 16th century, is given by the papal bull, and here are the words, and here is the 14th of the moon. I don't see how that can be construed as anything but a day, and then explicitly the day of the equinox. And so if we look at the comparison, that language is here in English, and except this I carried over as the Latin, the 14th of the moon, and the day of the equinox. And so in this picture, the granularity of a day, the day of the equinox, which is fixed here to March 21st, is a day. Luna 14 is a day, and so everything is a day. And so that's our picture. That's the chunks that we're looking at. If we go over to the Aleppo now, and this says it very explicitly that the first vernal full moon, and it is following the March equinox. And so we have this picture now where we're looking at instances, and I just put the March equinox here in the middle. I mean, it could be anywhere in the day, but the point is that this moon, this instant of the full moon, will become the part of the Paschal full moon, and that month is the month including Pascha. On the other hand, if the full moon were to occur here before, not after the March equinox, then this would be a case where this is not the month, and so we would have to wait then for another month. So this would make a big difference in timing, just by virtue of whether or not we're considering an instant or the day. In this picture, this would have been the day of the 14th day of the moon, or the full moon, however you're looking at it, because the granularity is a day. And it gets even a little more complicated, because then we have to go back to the calendar we constructed way back and say, well, what day are we talking about? Is it going to be the civil day, or is it going to be the biblical, the lunar day? And although they do overlap, they also have portions which are excluded one from the other. And this is something, too, that came up even in a more involved sense with that comment I did. It was as an aside, and it was that the Father Ziegler, in this paper that he submitted for the Gregorian anniversary, asked the question, and it's a reasonable one, is this principle of the new moon after 6 in the evening being followed? And he's asked that about the Gregorian reform itself, but also about the data of Professor Ledorlet, which he had looked at, and that professor's data is the one that we have also looked at as part of the Synodica 5 and the Chambesi calculations that were the astronomical calculations that were done explicitly for the considering the new method, and that were reported in the Aleppo agreement. And so that here we're asking him now about this, but that's really a very subtle difference. And as a matter of fact, I don't think that applies at all here. I think already in this picture is definitely looking at the civil day for the sake of comparison, but I could be wrong, and that's something that we would have to take a little more look at to be sure. Well, we're leaving behind now the granularity and taking a look at the accounting for the sun, and that's done through the leap year rules. And we're going to use the example, take a closer look at the revised Julian calendar, which Milankovitch in the 1920s announced in his paper that was the end of the Julian calendar and the new calendar of the Eastern churches. Before proceeding, I want to correct that. It's leap year rules, and we're going to take a look at the tropical year. So here is the textbook definition, and that's for us to contemplate. So this is theoria, but in terms of practice, how we're going to proceed forward, our action, we're going to take a look at the fractional number of days that the calendar tries to match in order to keep the seasons at fixed times. And it's going to do this as best it can. So there will be residuals, but they need not be errors if we keep them small. We need to compare leap year rule values, and to do this, we're going to use a mean, an average over many years, which will give us a 365-day year plus some fractional amount of days per year. And just to give you a reference, this is where we are in terms of the various phases, the calendar construction using arithmetic and the whole numbers and fractions. And there are at least two values for the mean year that we need to take a look at. They differ by very little. And the way I like to proceed is to only look at the decimal fraction amount, because they're both going to be 365 days. And so for one, it's the mean tropical year, and the other one is the vernal equinox year. And what I've done here is just to make these bigger to show that they agree to the thousandth place. So there's a very small difference between the two. And these are averaged. The difference is that the mean tropical year is averaged over all seasons, whereas the vernal equinox year is just averaged over the one equinox, the vernal. And the argument is that this is the more relevant one if you're trying to formulate a calendar where your emphasis is on keeping the date of Easter fixed. So how do these leap year rules function? And now proceed to how the leap year rule is going to function. And what we want to do is construct that fractional part, which is the number of leap days included over the number of years involved. We want them to best match the one of the two decimal fractions, and these are the two values that I carried over. And over here we have a number of calendars or proposals for leap year rules, and here it is given as the number of leap days included per number of years involved. And if we work these out to their decimal fractions, are these values, which we now compare to the two mean values for the tropical year. And here's the difference, and here it is as an absolute percent difference. So I just want to see how big it is in a relative sense. And for the mean year, the Julian calendar has a pretty big error. It's improved significantly by the Gregorian. Milankovitch improves it even further. But here's Stanojevic, and he improves it even more. And he's a Serbian also. There's an argument going on here. Well, why not use this value? And we'll get to that. And then the Persians. And remember Ignatius, Patriarch Ignatius, who arrived when the Pope Gregory was doing the calendar reform. And he had proposed this value, but the reformers, the Calendar Reform Commission chose to keep to something more traditional in terms of looking more like the Julian. And so it didn't proceed this way. And that produces a very good value also. But the winner, clearly, here is Stanojevic. Now, if we go over to the vernal equinox year, for that very small difference, we see something they stack up a little differently. Once again, the Julian is quite large. The Gregorian improves it significantly, and the Milankovitch value is actually bigger. So it's not as good comparison for or it's not as good an estimate of the year if it's the vernal year. Stanievich gets a little bit bigger even, but once again, the Persians really knock it out of the park. So it's a very small value. They would be the best for this comparison, and Stanievich or Milankovitch for this comparison. It's also a case that there's a certain art involved in formulating these and getting nice numbers, but to be able to go from a decimal fraction to a ratio is straightforward, and every rational number is either a terminating or repeating decimal fraction. That's this, and if we invert that, we can say that if we have a decimal fraction, there's a little mathematical machine called continued fraction, and that allows us to then produce a ratio. And the only issue there is that the ratio we get might not be a very nice one in terms of trying to formulate a leap year rule. To illustrate how this works and the effect it has, we'll take a look at the Julian, Gregorian, and the Persian rules. And for the Gregorian calendar, again, the idea is we want to keep, for all of them, we want to keep the value fixed at some calendar date around the March 21st. So here's 21 and a half. And every 4 years, we're proceeding to correct and then drift off, correct and drift off until we get to the century year, where the Gregorian has that correction, and that takes us, shoots over, but then again, every 4 years being corrected and drifting down, and then the next century year comes along and correction again. However, that's starting to drift up, and so the rule says that for the Gregorian, remember, if we hit the year 2000, well, we're not going to make a correction. So that's why we didn't advance another year from the 13 that's been in play. The 13-year difference between the Gregorian and the Julian, the 13-year difference has been in place since the year 1900. But we coasted right through that. We didn't make the correction, so we're still at 13. And then, but when it comes to 2100, year 2100, we're going to make that correction again. And then that's going to start going up, and so we'd have to make a correction after that. However, this right here is what the Julian calendar looks like all the time. And so what I've done is just taken this and cut and pasted just to give an illustration. Sorry about that. And what happens is it just keeps going and building up that error, and that's what we don't want. The other leap year rule that we wanted to consider is that the Persian one, and here is an illustration. That was 33 years, and it's relative to this mean value represented as 0 of the difference between the spring equinox and the beginning of the year, and that's you can see that holds that average very good. And look at the precision on that. We're here in the difference in hours, so it's plus or minus 10 hours. So that's very good, but that was rejected by the Gregorian reform because the emphasis was to keep things familiar and to still work. Well, how best to maintain the average and not have it be too troublesome? How often should leap year rule corrections be made? If it's too often, it becomes bothersome. If it's too irregular, it becomes difficult to apply. And there's one more comparison we want to make, and that is with the Milankovitch revised Julian calendar. And we're coming into the home stretch here. Milankovitch wrote his paper and submitted it in 1924 in German, and soon after it was translated into English and reported in this journal, Popular Astronomy. And the translator, the translation starts here, but she mentions that it is a slight improvement over the Gregorian calendar. And another appraisal, this is a fairly well-known book about calculations involving the calendar. And there's our Hill of Spring again. And in a footnote, he mentions this as a slightly more accurate leap year rule. The revised Julian calendar, it's used, how it's used, and He says, like the rest of the world, we ignore this, in quotes, improvement. A little harsh, but looking now at an article in a scholarly journal that focuses on the tropical year and solar calendar, fairly recent, June 1991, and the author says that this result alone entitles us to state with confidence that our Gregorian calendar will not deviate from the exact solar calendar by significantly more than 1 day for some 2,000 years to come. Well, what's going on? And here is the Shields translation of Milankovitch. So these are just his words. And with regard to that controversy with Stanievich, what happened, I think, was that they didn't really want to see this calendar immediately presenting a problem of yet another difference between the Gregorian and the whatever the proposal is. And so, whereas the Stanievich would have meant that the difference would have occurred much sooner, for Milankovitch, that won't happen until the year 2800. So it's putting the problem in the future, but being concerned about this potential problem. And so these are his words. And he says, well, we can compare this to the Julian calendar. So we have this every fourth year. So that's 1 in 4 or 1 in 400. Because I want to keep these the same comparison. However, for the Gregorian, it's a little different, and we take those 3 leap days out, and so we get 97 over 100. And here's our 2 numbers. Milankovitch now says that he's going to propose the new calendar, and this is the rule. Okay, so he's going to give us a ratio, but how do we put that? How do we implement it when we go to our calendars? And he says, well, when those whose first 2 digits, when divided by 9, give a remainder of 2 or 6. So this is a modular arithmetic. They're a little more complicated than the Gregorian formula. However, let's apply that. So what he says, by applying this leap year rule during the space of 900 years, he's choosing to do that. This is what happens. We have the Julian calendar, and he says we're going to remove 7 days from the Julian calendar over the 900 years. So that's what I'm going to do here. The 225 minus 7 over 900, and that gives the 218 over 900. When this was in the table, I just divided these 2 by 2. So in the table where I showed this, it was 209 over 450. Either way, it gives this value that we have seen before, and this is one of those repeating decimals. It just keeps going on 2 all the time. And I should have said dividing top and bottom over 2, 109 over 450. How does this compare to the Gregorian calendar? Well, here is the Milankovitch value again. And let's take a look here at the Gregorian calendar and the leap year rule. And remember, it's going to the paper said that in another 2,000 years. So let me just look at 3,600 years for convenience. 2,000 would take us to the year 4,000. And so what I'm going to do is take the Gregorian value and multiply it by 1. So I'm not changing anything. I get 873 over 3,600. What if 1 more leap day is removed in 3,600 years? So that's another correction. And let me do that. So I'm going to subtract 1. I get 872 over 3,600. If I now divide top and bottom by 4, again, I'm not changing anything. That's just an operation of a multiplication by 1/4, top and bottom. I get 218 over 900, which is exactly the Milankovitch value. And so if one more leap year correction is made on this basis of something like 3,000 to 4,000 years, I will be achieving in not so regular a way, the same value that would be gotten from the Milankovitch revised Julian calendar. And so what's going to happen is that these residuals will build up to be bigger, and then a correction will be made. The issue is, well, that won't be noticed. And so mathematically, it looks like it's a very significant improvement. But in terms of what we would experience on a day-to-day basis or a calendar experience, it wouldn't make that much of a difference. And likewise, that conclusion reached in the paper about the tropical year and the solar calendar is that the behavior of the Gregorian calendar during the 1 or 2 nearest millennia renders approaches to a calendar reform both premature and unnecessary. Well, in conclusion, words that we all want to hear, I was thinking again about that phrase from Jean Meus about the accuracy needed in calculation depends on its aim. And I thought about horseshoes and the old saying, close only counts in horseshoes, and I would add, and the computus. Because we don't necessarily always have to get a ringer. We are okay with a leaner sometimes, or just being close enough. And this, if this is a day, then we can get something that counts. But we certainly don't want that to be 13 days away. These are just some references that I've used and bring to your attention. They're all online. And the one I didn't use, but I would also recommend, is this from a very technical point of view also, but it's from an Orthodox perspective. It's in the International Journal of Orthodox Theology. And the author is both a deacon and a scientist. I was going to put this at the beginning of my talk, but I think it serves a useful place here as a summary. With hardly, I believe, an exception, we all experienced that strange phenomena of the almost inverse proportionality between the importance of many common factors in our lives and the degrees of attention that we give to them. Among such factors is the role of the calendar in our daily activities. How many of us give any attention to how and why the calendar is structured the way it is? Could it be structured otherwise, perhaps even better? Yet the calendar forms the basis for the rhythm of our various daily activities. Do we reflect, for instance, that the duration of the hour and the length of the week have no basis in natural astronomical phenomena, even though both are of very long usage? The week, in fact, is the only calendar period which has survived all calendar reforms without interruption. On the other hand, the 3 natural periods are the day, the month, and the year, arising from the relative motions of the earth, moon, and the sun. The incommensurability of these periods is the fundamental reason for the long and continuing history of calendar reform. The rhythms of human life are dependent upon the rhythms of the universe. There are those who rightly point to Isaiah and St. Paul, admonishing us that we do not elevate a regimented observance, a law of the calendar, making it into a substitute for the law within, the law that is written on our hearts. Knowing that, we rightly hymn the guidance provided for us by God, who made the moon for the appointed times and the sun that knows its entrance. And God saw everything that he had made, and behold, it was exceedingly good, very good, very beautiful. We, mankind, Adam, were created on the 6th day along with the beasts and creeping things, but also in the image of God, after his likeness. And we have that perfect image and likeness, who for us men and for our salvation became man. O most holy Trinity, have mercy on us. O Lord, cleanse us of our sins. O Master, forgive our transgressions. O Holy One, come to us and heal our infirmities, for your name's sake. Amen.